Hello students, how are you? Good morning. I hope you are doing well. Okay, so here we are with our question discussion session on KTG and thermodynamics. And this is our first session on this chapter. Okay, so what we are going to do, we are going to take some numerical problem, some conceptual problem, some PYQs, okay, and try to understand the concept behind this chapter. Because usually this chapter may seem tough to the student, specifically thermodynamics. Okay, so we will see that which type of question can be asked from this chapter and how to solve them and what are the concept behind. Okay, so let us solve our first question. Just a second. So this is the very first question on your screen. Before this question, I want to discuss some of the basic concept of thermodynamics, in which the very first that is come to your mind is work done. So work done in thermodynamics is given by integral of P dot dV. Where dV is not the velocity, it is the change in volume, and P is the pressure. Now, instead of writing this, you can also write it as d of PV, which means whether it is pressure is a variable here or volume is variable. Based on that, you will calculate this work done. Okay. If change of volume and pressure are constant, then work done you can directly give P into delta V. If volume is not changing but pressure is changing, the same will be given by V into delta V, or V dP. Got it? If P is changing. Got it? Although there is an indicator diagram here that is drawn between pressure and volume, is termed as indicator diagram. Indicator diagram. The indicator diagram key, what is the characteristic of that? If this is the variation of pressure with volume, so if you calculate the area under this curve, this, so this area of PV curve P equals to work done, because you can see easily whatever be the change in pressure or whatever be the change in volume, they go to multiply to calculate the area of this. And in work done is also is this P into delta V. So we can say that this graph gives you the work done. Okay, although the variation of pressure here is not constant, so we would consider a strip where the variation is constant. Yes. P2 P plus dP. So So for that, you can consider the pressure to be constant, and this should be dV is the change here. Okay. So what is the area of this strip? So it is given by P into dV. So if you integrate it, you will get to know the total work done, and which is nothing but the area of indicator diagram. Okay. This is it for this numerical. Now in this numerical, in any thermodynamic process, pressure varies as, and pressure is given in terms of Pascal. So pressure varies as P is equals to A into volume plus B, where A and B are the constant, and V is the volume here. Now we have to find out the work done by gas during expansion from 1 meter cube to 2 meter cube. This MC is nothing but meter cube. Now, if we try to solve this question, what do we need? Firstly, the variation of pressure is given to you in terms of volume. So you can say that pressure is not constant here. Pressure is varying according to volume. So for that, in that case, what we have discussed, if we want to calculate the work done, we have to take the very small change of volume. So that is the differential work, which is dW is equals to P into dV. Now, if you integrate it, then you will get to know the total work done. Okay, so we know and put the value of pressure here. That is AV plus B into dV. Now, volume varies from 1 meter cube to 2 meter cube. This will become A 1 to 2 VdV plus 1 to 2 BdV. Now, B is a constant, so you can take it out. So this expression finally results in A V square by 2, limits are 0, 1 to 2. Okay, plus B into V 1 to 2. Now, now put the value of limits inside it. That is upper limit, which is 4 by 2, minus lower limit, which is 2 by 2, which is 1 by 2. So plus B into 2 minus. Now this will become A into, this will become 2. 2 minus half will become 3 by 2, plus B. This will become 3A by 2 plus B. This is the work done by the gas during expansion from 1 meter cube to 2 meter. Now this is the expansion, means work is done by gas, and gas is our system. So in that case, this work done will be considered positive. Positive work done. Why? Positive work done. Why? Because work is done by the system or by the gas, which is our system. Okay. Now move on to the next question. This is the PYQ based on indicator diagram. So here a thermodynamic system is taken through a cyclic process. The total work done in this process is, this is the question. Now a PV diagram is given to you. So we know that total work done is given by area under PV curve. So we are only interested in this area because this is a cyclic process. So this bound the area. This area is bound. You do not need to consider this area. Okay. So this area we will not consider. This will consider this area, not this. Okay. Because this is the area under these curve. No? Okay. So we are only interested in this. So clearly it is it has been seen that this area is nothing but a triangle. So total work done here will be total work done area under PV curve. So it is clearly 1 by 2 base into height. Now what is the base? Base is this. So it is 2 to 4, which means 4 minus 2. Note take, generally what student do, they will take 4. No, base is only here to here, C to E. And C to E we have cover only 2 units. So this will be 2. Now same case with height. So in height we have moved from 100 to 400, which means 300. Difference is this. So CD is nothing but 300. This will cancel out. It will give you 300 joule of work. Okay. So this is the work. Now, if you if in this same question it is given to you, this is like suppose this is the MSQ multiple select question, and in that MSQ internal energy is also being asked. Now, what is the internal energy and heat input? Internal energy is also being asked. Now we know that internal energy is a state function. Okay, it is a state function. So it will only depends final and initial coordinate. Final and initial state the system. So if it is depending only on the final and initial state of the system, so internal energy you can say here is equals to 0 because the final and initial state are same. The system has moved from D to E, then C to E, and then it come again to D by this path. So this is the cyclic process. So for cyclic process, delta U is to be 0. Now how to calculate the heat input? So according to first law of thermodynamics, delta Q is equals to delta U plus W. Now if it is 0, then delta Q is nothing but W, which is 300 joule. Okay. This process may all the heat that we have provided is going to completely change the or is completely going into doing work, not the change in internal energy. Now, this one. Now, in this question, the initial pressure and volume of an ideal gas are P node and V node. The final pressure of the gas when gas is suddenly compressed to volume V naught by. Now, whenever there are two processes, isothermal and adiabatic. So for adiabatic, adiabatic process is very fast. Adiabatic process, this adiabatic process is very fast. So in case in any question, if you will find out these terms suddenly compressed, suddenly expand, suddenly removed. So this sudden means this process is going to be very fast. Very fast this process is going to take place. Okay. So if this process is very fast, so you can put this as adiabatic process. Okay. So try to find out these types of keyword in a particular question. Okay. So in this question, initial pressure and volume are P naught and V naught. These are the initial pressure and volume. Okay. Now the final pressure of the gas when gas is suddenly compressed to a volume V naught by 4. So we can say that P1 or this process is adiabatic because this process is going to be very fast. So we can consider it to be adiabatic process. So for adiabatic process, we know that for adiabatic process, we know that PV raised to the power gamma is constant. So for this process is to be P initial, V initial raised to the power gamma, P final, V final raised to the power gamma, where gamma is the ratio of specific heat at constant pressure and constant volume, and it's also termed as adiabatic index. Now, P initial is P naught, V initial is V naught, P final is P final, let's say, and V final is given to you V naught by 4 because the gas is compressed to this volume. Okay, so P naught V naught raised to the power gamma PF. If you distribute this power, it will become V naught raised to the power gamma divided by 4 raised to the power gamma. This will cancel out. So final pressure that you will have P final is P naught into 4 raised to the power gamma. So this is the final expression for pressure that you will have during this process. So option D is the okay. Now the thermodynamic conceptual question or theoretical question is you may accept one or two theoretical question from thermodynamics. Okay. The thermodynamic process in which internal energy of the system remain constant is. So we know that in isobaric process pressure is constant. In isochoric process volume is constant, or I will say change in pressure or change in volume is constant. In adiabatic process delta H, or let's say delta Q, is equals to constant. No heat is given or transfer from the system or into the system. Isothermal process में we have the change in temperature as constant. The change in temperature is constant, which means there is no change in temperature during this isothermal process. So now, if I talk about the internal energy, okay, of a system, so we know that this delta U is nothing but NCV delta T, or constant volume, sorry, for this. So from that expression, you can say that delta U is directly proportional to change in temperature somehow. Okay. Although in another explanation, you can say internal energy of a system, specifically if it is a gas. So it is nothing but the kinetic energy of the system, because gaseous molecules are always in motion. So we can consider that all the internal energy possessed by the system, which is gas, is nothing but the kinetic energy of the system. And kinetic energy of the system is given by 3 by 2 kb into T, which is again is depending on temperature. So we can say that internal energy, internal energy depends on depends on temperature. Now, if the in all these process that is given in the option, nothing in any process, it is not said that in these three processes that temperature is not changing. Here the pressure is not changing, in isochoric volume is not changing, adiabatic heat transfer is not changing, but we cannot say anything about the temperature. Okay, whether it is changing or not. But in isothermal process, we specifically focus on the change in temperature. And in this process, the temperature is not changing. So if temperature is not changing, the internal energy will also not changing, because internal energy depends on the temperature. So according to the question, in which internal energy of the system remain constant, what is that thermodynamic process? So that thermodynamic process be isothermal, because in isothermal process there is no change in temperature. It results in no change in internal energy. So internal energy will remain as it is, because the temperature is not changing. Okay. Now, the same way in this question, a gas is compressed adiabatically. Which one of the following statement is not true? So in these types of question, try to read the question once again, at least 2 times, so that if you find anything true, you will tick it. But in this question, the option is to, the work is to select not true statement. So if I talk about the first statement, there is no heat supplied to the system if it is compressed adiabatically. So adiabatic is the process here in which change in heat is equals to constant, or you can say zero, because there is no heat you can give to the system and no heat you can transfer to the system. Although in this way we can say that change in pressure is zero, volume is zero, and heat transfer is zero. Okay. So delta Q is zero here because there is no heat transfer in adiabatic process. So you can say this option is correct. There is no heat supplied to the system. Now, if one who not study, who not read this question carefully and take this answer because this seems to be correct. So it will correct this option and made a mistake. So our job is to find no true statement. So this is not our option. Now the temperature of the gas increases. Obviously, if the gas is compressing, if the gas is compressing and there is no change in according to first law of thermodynamics, delta Q is delta U plus W. So if this is zero, delta U should be equals to negative of work done. Okay. So all the work done which is going to compress the gas will automatically increase the internal energy. An increase in internal energy will result in increase in temperature because delta U is directly proportional to delta T. Okay, so this is also correct. This cannot be said that it is not correct. This is the correct statement. Option C says that there is no change in the internal energy. This is also not correct. Okay, this is not true because if the temperature of the gas is increasing, then how it can be possible that internal energy is not changing? This you can say here, this statement is not true. This is not true. So we have to correct this option because this is not a true answer. Okay. But if you will see the change in the internal energy is equals to the work done in this process. So yes, from this statement you can say this. Now this in this question consider two containers A and B containing monoatomic gas at the same pressure, volume and temperature. Same pressure, volume and temperature, which means the initial pressures, initial volume and initial temperature of both the gases are same. Now the gas A is compressed isothermally to 1 by 8 of its original volume, while the gas B is compressed adiabatically to 1 by 8 of its original volume. The ratio of final pressure of the gas in B to the gas in A. Now this gas is monoatomic, and because there is a term adiabatic is used here, so in that adiabatic process we need to know what is gamma for monoatomic gas. So gamma for monoatomic is 5 by 3. Okay, so it is gamma for monoatomic is 5 by 3. Now for gas A, for gas A, if you will see, this gas A is compressed isothermally. So for isothermal process, we say that P1 V1 is equals to P2 V2 because temperature is constant. So PV is equals to nRT. This will also become constant. So we can say PV is equals to constant, and from that we drag this relation which is P1 V1 equals to P2. Now this is for A. So P1 into V1 P2 into V2 is 1 by 8 to the original volume initial. This will cancel. So P1 here is P2 by 8 and this is for A. Now, or you can say P2 for A is 8 times of P1. Now for gas B, we can say that this process is adiabatic, so PV raised to the power gamma is constant. So P1 V1 raised to the power gamma, P2 V2 raised to the power gamma. Now P1 is P1 and V1 is V1 because initially A and B containing monoatomic gases at same pressure, volume and temperature. So V1 raised to the power gamma. Now P2 of B, which is different final pressure. V2 is 1 by 8 of V1. If you distribute the power in the RHS side, so you will have V1 raised to the power gamma, 8 raised to the power gamma. This will cancel out. So P2B, you will have 8 raised to the power gamma into P. Now P2A you will have as 8 times P1 and P2B you will have as 8 raised to the power gamma. Now gamma for monatomic gas is 5 by 3. So it is 8 raised to the power of 5 by 8 you can write as 2 raised to the power 3. So it will become 2 raised to the power 5 which is 32. Okay, gamma into P. Now in the question the ratio of final pressure of gas in B that of gas A is being asked. So we will take the ratio P2B divided by P1B 32 P1 divided by 8P. And this will cancel out. This will become 4. So this ratio that we have is 4. Okay. Now this one. This is the another type of question that has been asked in thermodynamics frequently. Okay. And these types of question are based on the efficiency of an engine or specifically the Carnot engine. Now work done by a Carnot engine operating between temperature 127 degrees Celsius and 27 degrees Celsius is 2 kilojoule. The amount of heat transfer to the engine by the reservoir is. So we know that Carnot engine has the maximum efficiency. Okay, and that heat engine is run between two thermal reservoir, one of at high temperature and one of at low temperature. This low temperature source of heat is termed as sink and this is termed as reservoir. Thermal reservoir or hot reservoir you can say. Okay. And this is the work done itself. Now this Carnot engine operating between 127 degrees Celsius and 27 degrees Celsius. Now The important thing is that you need to convert this degree Celsius into Kelvin. So we know that 1 degree Celsius equals to 273 Kelvin. Okay, sorry, 0 degree Celsius. Or simply I will write the relation here that T in Kelvin is equals to T in Celsius plus 273. If you want to be more precise, that it is given by 273.1516. Okay, now so T in Kelvin will become, for this 127 degrees Celsius, 400, and T, this is for hot and this is for cold. So there is a difference of 100. So if you subtract 100 or just add 273 plus 27, it will give you 300 Kelvin. So this is at 300 Kelvin. This is at 400 Kelvin. Okay. Now the amount of heat transferred to the engine by the reservoir we need to calculate, and work done is given to you 2 kilojoule. Now we know that eta of Carnot engine is by given by 1 minus T of lower temperature, T of higher temperature. Eta will be 1 minus T lower is 300, T higher is 400. So this will become 1 by 4. Now we know that this eta of Carnot is nothing but work done by heat transfer. Okay. And this eta is to become 1 by 4. Work transfer is given to you 2 kilojoule divided by Q. So Q here will be 8 kilojoule. Okay. So this 8 kilojoule heat you need to transfer to get a work done of 2 kilojoule only, and 6 kilojoule will be rejected to the hot, sorry, cold temperature or sink. Okay. Now this question. In this question, there are two statements are given. First is if heat is added to a system, its temperature must increase. Okay. And the second statement is if positive work is done by a system in a thermodynamic process, its volume must increase. So we will just justify these statements. If heat is added to a system, this temperature must increase. Is it correct? No. It is not possible for all the cases, because if we talk about adiabatic process, adiabatic process, in this process there is no heat transfer. No heat transfer. So if there is no heat transfer, according to this statement, the temperature is not increases. Okay. But we will see, we have seen that in adiabatic process, the change in temperature is possible. But the change in temperature is possible. So if the change in temperature is possible, which means I'm compressing it, the temperature will increase, and in expansion, the temperature will decrease. So which means that without adding heat to the system, the temperature is increasing or decreasing according to the expansion or according to the types of type of process that you are doing. Either you are doing compression or you are doing expansion. This statement is not true for all the cases. Now, verify this one. The positive work is done by the system. Let us consider a system. Here, this piston and cylinder arrangement. This is the gas bed. Now, our system is this gas, okay? So, if the gas is doing work on the piston, what will happen? The piston will move up and gain a new position before the initial position, okay? And this will be the increase in volume, okay? So yes, if the system is doing work specifically, then the volume must increase. So this statement is correct because gas will expand, then in an expansion there is must increase in volume. So statement 1 is false, but statement second is okay. Now this one, source supplies heat to a system at the rate of 1000 watt. Rate. Here the rate is given. If the system performs work at a rate of 200 watt, the rate at which internal energy of the system increases is. And that is why, because in the question rate is given, that is why the unit is watt here. This is a very simple question. What we are going to do according to, because where do you find these three quantities connected? Heat, work, and internal energy in the first law of thermodynamics. So according to first law of thermodynamics, according to first law of thermodynamics, we know that dq is equals to du plus dw. Okay, so for that, what you can say, if we are interested in the rate, because rate is given to us, so we will differentiate this term with respect to time. So it will become dq by dt du by dt plus dw by dt. Now dq by dt is given to you as 1000. Du by dt you are interested to find out, and dw by dt is given to you as 200 watt. So du by dt is equals to 800. Look how simple this question is. 800 watt is the correct answer. Now, this one, again based on Carnot engine and efficiency of Carnot engine. So a Carnot engine operating between two reservoirs has efficiency 1 by 3. When the temperature of cold reservoir is raised by x, its efficiency decreases to 1 by 6. The value of x if the temperature of hot reservoir is 99 degrees Celsius. Now we will consider a hot reservoir. This is the hot reservoir at 99 degrees Celsius. So T Kelvin will be 99 plus 273. It will become 9 plus 3 is 12. 9 plus 7 16 plus 1 17. 2 plus 1 is 3. It is 372 Kelvin. This is the heat engine. Work is done here. And then we have the cold reservoir. Okay. So heat, we extract some amount of heat, we reject some amount of heat to this. Efficiency is firstly, the efficiency is 1 by 3. Okay, we do not know anything about the reservoir of cold temperature. So initially we will consider it T. Okay, now the efficiency is given by 1 minus T of lower temperature, temperature of lower reservoir or cold reservoir, and temperature of hot reservoir. It is 1 minus T upon 370. Now n is given to us 1 by 3 initially. So 1 by 3, 1 minus T by 372. Take this on this side and this one on this side. It will become T upon 372, 1 minus 1 by 3. T upon 372 will become 2 upon 3. We will cancel this out. 3 1 is 3, 3 2 is 6, and 3 4 is 12. So temperature of cold reservoir when the efficiency is 1 by 3 will become 248 Kelvin. Okay. Here. But this is not our answer. Now this value of the cold reservoir temperature is increased by X. Then the efficiency decreases to 1 by 6. Now the efficiency will become 1 by 6 when temperature is increased by X plus the temperature of hot reservoir is not changing, so it will remain as it is. 1 by 6 is equals to 1 minus, this will become 372 plus, sorry, this will become 248 plus X divided by 372. Now 248 plus X divided by 372 is equals to 1 minus 1 by 6. 248 plus X divided by 372 is equals to 5 by 6. Now we will cancel this one. It will become 6, 6 is 36 and 6 to 12. So X 248 plus X is equals to 5 times of 62. It will become 5 to 10, 5 6 is 30, 310, 248 plus X. X is equals to 310 minus 248. Finally, it will become 62 Kelvin. So the temperature of cold reservoir is now 62. Now that X is nothing but 62 Kelvin, which means the temperature of the cold reservoir has been now increases to 310. Okay, that is why the efficiency is decreasing. So 62 is the correct option. Okay. So this is it from my side. If you have any kind of doubt, you can connect to me and put this in the chat box. Otherwise, the lecture is being over. Thank you so much for being attentive. Thank you so much.